Welcome to course on tribology. The first lecture, Introduction to Tribology. First question comes in our mind, what is the meaning of tribology? Is it related to tribals? Is it related to any way some village related thing? In real fact, it is not. It has been derived, or this word has been derived from the Greek word tribos. Meaning of tribos is rubbing. So, we can say the tribology is science of rubbing, and this is one of the easiest meaning or easiest definition of tribology. However, a slightly difficult definition is that tribology is a science that deals with the friction, lubrication and wear of all contacting surfaces. Here, meaning of the contacting surface is that the two surfaces which are in intimate contact and subjected to load have some relative speed. So, contacting pair having relative speed subject to the load comes under the tribological field. Now, we need to understand that subject or those contact pair using tribological knowledge. As I mentioned, it is a slightly difficult definition. Reason behind is that friction itself is a statistical parameter. We can never get constant value of friction, even though if we repeat experiment again and again, we will never get constant value. We can get some mean value and some standard deviation, and ratio of mean to standard deviation will always vary depending on whether there is a direct contact, mixed lubrication or full film lubrication. Better the lubrication, mean to standard deviation value will increase. Another point is that we are kind of the mechanism, we have too many mechanisms, maybe more than 32 mechanisms. So, understanding all those mechanisms are slightly difficult. That is why we say that this is slightly difficult definition. And lubrication science itself is a complete subject, and we need to merge friction, wear and lubrication in one subject. That is why it is slightly difficult definition. However, if we understand friction, wear and lubrication, get some knowledge and apply those knowledge to the real machine components, it will lead to improved service life, improved safety of the components, increase the reliability of the system. So, if we are able to achieve all this, naturally there will be drastic or substantial economic benefits. So, you can say this tribology is most important for all machine elements. We need to understand these machine elements, science related to friction, wear and lubrication of those mechanical elements. To get a better feeling, let us start with a few examples. First example which I am showing in this is a carbon graphite seal. This carbon graphite seal is made from powder by compacting and sintering that powder, and when it comes into contact with a stainless steel shaft or some other material, there is a possibility of intimate contact, relative sliding and applied load. So, it makes a tribo pair. You can see there is some mark, some disruption on the surface. It appears some material is removed from this surface and transferred to some other material. This is known as adhesive wear, occurs because of tribological phenomena, but it can be delayed, it can be retarded, it can be reduced by proper knowledge of the tribology. And if we can reduce that, this kind of surface, irregular surface can be reduced. That will reduce smoother roughness, increase smoothness, and if there is a smoother surface, more and more contact, then there is a possibility of lesser stress. If there is a lesser stress, serviceability will, service life of the component will increase. Another view, if I make extra smooth, absolute nanoscale smooth surface, that will also cause some problem. So, we can say there is always a trade off between roughness and smoothness, and understanding that trade off, we require good tribological knowledge. So, we require this course. This is what I have been shown earlier. There is adhesive wear. We call it adhesive wear because occurs because some intimate contact between two surfaces and then removed from one surface to other surface or transfer from one surface to other surface. Let us take another example. There is a cam. We know cam is used to impart rotary motion, and cam follower pair can be used to change rotary motion to the sliding or reciprocating motion. When cam failure occurs or occurred in one toothpaste company, toothpaste factory, where this kind of the pitting failure occurred. These pits were generated because of the fatigue wear. We know very well, if we drive car on irregular surface, there will be a lot of noise, vibration that will cause fatigue. Same thing happened in this case. Due to irregular surface, obviously the number of pits, noise generation increased, that caused machine failure. That can be avoided if we have proper knowledge related to tribology. And this can be named as this figure can be named as a pitting wear of cam surface. Let us take another example related to journal bearings. We know journal bearings are used to support radial load. Generally, they have infinite life if they are properly designed. I have shown the two figures. Left hand side figure is bearing of an IC engine, what you call as a crankshaft bearing. You can see the number of scratches on this bearing surface. What we know in term this as a abrasive wear. While right hand side, there is another aluminum bearing, is also a journal bearing. You can see there is a more amount of the wear, what we call as a rubbing wear, where the shaft touches to the bearing surface and runs along with that, try to scratch the surface with more contact. We can say this kind of wear occurs when there is a heavy load on the bearing or relative speed is low, sliding speed is lesser than desirable. This kind of failures can be avoided by enhancing the relative speed, reducing load or filtering the lubricant, but we require proper knowledge to target those aims. So, that is why we require tribology course. Let us get another example of magnetic bearing. See, magnetic bearings are known for non-contact levitation, zero wear. We did this experiment in our lab, assuming that permanent magnetic bearing under repulsion levitate shaft without any contact, but it did not happen. Shaft was tilted, its own started edge loading on the bearing surface, and due to that edge loading you can see there is an enormous wear. So, it is not only the levitation failed, but even it caused a much more wear compared to an ordinary non-magnetic bearing. So, we required good knowledge, good tribological knowledge to design this kind of components. We can name this figure as a wear scar due to edge loading. As I mentioned, shaft tilted is shown under operating conditions and cause edge load. We did not impose any side load in edge load in that, it happens is shown under operating conditions. Let us take another example. This multi-row roller bearing is more 4-row roller bearing. and I am showing only the figure of outer ring where cracking happened under severe operating conditions. You can see there are deep cracks, through and through cracks. Now, these cracks happen if we do not mount bearing properly. So, this bearing failed because of improper mounting. That can be avoided if we go through tribology course, understand physics of tribopairs, and we can really avoid the failure of this big roller bearing, which cost huge amount. It is not only initial cost, but stoppage of cold rolling mill cost much more production loss. So, the overall much higher loss compared to bearing cost itself. There is another figure here, we are showing the gear failure. This is a SEM picture of gear tooth. You can see there are one pit, second pit, third pit. So, this happens near the pitch circle diameter, just below the pitch circle diameter. Due to this kind of pit generation, gear operation generates a lot of noise, and which is generally not acceptable by customers. So, we need to open assembly gearbox and replace this gear. That means, this pit is causing reduction in service life of gears. That can be avoided by proper lubrication. If we understand lubrication properly, we can avoid this kind of failure, or we can reduce this kind of failure, or we can say enhance the life of the components. So, this is shown the pit, and we can label this figure as a pitting failure of gear surface. Apart from these examples, there are a number of other examples, number of other kind of the fluid film bearings. There are more than 20,000 rolling element bearings, number of seals, elastomer, polymer, ceramic seals, cams, various kind of the cams, and the brake materials. Every of this component involves some tribology, and we need to understand tribology to do a better design of these machine elements. So, we can say if we understand the basic knowledge, we gain basic knowledge of tribology, that will be helpful in industries like power generation industry, steel, cement, oil industries. Apart from these major industries, even we can use the tribological knowledge in household appliance, as well as very big machine components or big machine assemblies like ships, aircrafts. As this course is highly related to the practice industry, that is why many times this course is known as industrial tribology, applied tribology. So, once again welcome to this course. I believe I have conveyed the meaning of this course, importance of this course. Let us just go back how this course is started. How this topic was coined in somewhere in 1964. There was one conference in UK, Cardiff, where most of the engineers, service engineers from iron and steel industry participated. They expressed failures which happened in their industry, and to surprise, this kind of failure happened because of lack of knowledge related to the lubrication, related to the friction and wear. These points were conveyed to UK Minister of the Science, and he wanted to reduce this kind of losses. So, he formed a committee to look into those matters related to friction and wear of those industries. This committee took almost 2 years and gave final conclusion that reduction in frictional wear of iron and steel industry machine components is not an easy task. It requires interdisciplinary approach. It requires knowledge related to solid and fluid mechanics, chemistry of lubricant, material science of surfaces, bulk materials also. So, that interdisciplinary approach was essential to address problem raised in conference 1964, and there was no common word available. The committee chairman Peter Jost contacted Oxford in dictionary people and then came up with the word tribology. As I earlier mentioned, the tribology is derived from the word tribos, which mean rubbing. So, that is the easiest definition. Science related to rubbing is tribology, but difficult definition is this course, this topic is related to friction and wear of contacting surfaces, which involve a number of difficult topics. To continue this course, after 1966, when the term was coined, wherever people have given mechanisms governing interfacial behavior, that mechanism was termed as a tribological mechanism. Wherever the theories were used to quantify interfacial mechanisms, theories were related to tribology. Wherever solutions were given to reduce friction and wear problem, solutions were termed as tribological solutions. Major development happened in somewhere in 1980s due to development of scanning tunneling microscope that provides good surface roughness profile and non-contact surface roughness profile without damaging to the surface. However, one major drawback of this STM was the conductivity. It required material to be conductive. So, it could not be enhanced, it could not be used for almost every material. However, that was satisfied in 1985, where the development of AFM, or what we know as atomic force microscope, was developed. Major purpose, major aim of AFM is to measure the surface topography, and with some addition it can be used for the friction force measurement. With providing a number of tools, this kind of instrument can be used to study adhesion, which causes adhesive wear, adhesive friction, scratching, which causes abrasive wear, some other wear mechanism like fatigue wear, corrosive wear, lubrication, thin or thick lubrication. It can be used for finding elastic and plastic mechanical properties of the surfaces. So, after 1985, we can say that a big boom came in tribological field, where these components were used extensively to study almost all tribal pairs. To understand those tribal pairs, enhance efficiency of those machine elements and get overall economic benefits. Interestingly, this course has been taught in number of engineering colleges and science colleges at the elementary level. Only problem is that this course has been taught at very basic level. The meaning of the basic level is that most of these laws which were given or written in books are based on experimental results. It's something like friction force is proportional to normal load, or another word, if friction force is constant, normal load is constant, coefficient of friction will remain constant irrespective of temperature condition, irrespective of lubrication conditions, which is absolutely wrong. This kind of sentences or this kind of laws are applicable in very narrow domain. Let us take an example. We say static coefficient of friction is always greater than kinetic coefficient of friction, but it is only used for the metals. For most of the polymers, static coefficient of friction is lesser than kinetic coefficient of friction. With higher velocity, higher coefficient of friction occurs. So, these laws which we studied in earlier classes, they are restricted to very narrow domain. They cannot be applied in general. So, we require a course where we can understand these laws and we can utilize for almost all machine components. Another problem is that why this course has not been taught in earlier engineering colleges and science colleges. One reason I can state is that this course is slightly complicated and it interconnects a number of subjects. Getting mastery in number of subjects and then teaching that course is slightly difficult. That is why it has been always avoided. But we require to integrate knowledge gained from solid mechanics, fluid mechanics, chemistry, material science, etc. in one course, and that is why we are proposing this course, so that overall economic benefit can be achieved, student learn and then apply on machine element components. As I mentioned that we want to integrate number of subjects in one subject. Initially, we need to think what are those subjects. I can broadly say that there are 4 subjects which we need to integrate in one subject. One is the solid mechanics course, fluid mechanics, material science and chemistry. Solid mechanics is generally related to the forces, stresses, strains. We will be interested to find out what are the contact stresses as a function of surface temperature during sliding. Now, this can be contact can be between 2 convex surfaces, convex and flat surface, convex and concave surface. Interesting thing about this subject is that what we generally treat as a point contact or line contact, it never happens. It is always a surface area contact which need to be examined properly to get overall good results. When you think about the fluid mechanics, we are more interested to find out, will there be any fluid film between contacting pair? If there is a fluid film, we know contacting surface can be avoided or contact between 2 surfaces can be avoided. That will help minimizing wear, reducing the friction and bringing more and more stability in friction experiments. In other words, if the surface is lubricated, friction behavior will remain by and large almost same level with slight standard deviation, but if the surfaces are under dry contact, then there is a more chance of friction variation or standard deviation, the values of friction will be higher. Similarly, material science, it deals with atomic and microscale mechanism. We understand how surface is degraded. If we understand the surface degradation, then we can modify our fluid mechanics and solid mechanics related theories and get better and better results. Final subject which we are planning to integrate is the chemistry. We know the lubricant have some chemical form. We want to know whether those chemicals will spread uniformly on the surface, will attach to surface strongly. If it is possible, then requirement of the lubrication or re-lubrication will reduce. That will help us in reducing overall cost required for lubrication or re-lubrication of the surfaces. So, we are planning to integrate these courses in one course named as a Tribology. Some more detail about these subjects, the solid mechanics. We say that solid mechanics is related to the applied force. Under application of force, material may behave as elastic material, may behave as a viscoelastic material, or may behave as a plastic material. Generally, we distinguish between these material based on storage and loss modulus. If very high storage modulus, we can say the material is elastic. Very high loss modulus, we can say the material is viscoelastic or viscous nature. What are the important topic in this subject is something like a word Hertzian contact. We need to find out what is the Hertzian contact pressure, what kind of stress it will develop. But this is also related to the surface roughness. By changing the surface roughness, Hertzian contact pressure can be changed. As we know, changing surface roughness will change real area of contact. So, that will change contact pressure. Sometimes we require thin layer modeling of the solid surface. If the top layer is behaving different manner compared to the bulk material, solid mechanics to some extent will be related to the heat source because of the heat generation due to friction and heat getting conducted away from the surfaces. So, we will involve the heat equation to get overall good results. In addition to that, we will be using some sort of fracture mechanics, where we need to understand how crack is nucleated, under loading condition how that crack propagates, and finally delaminated from the surface. So, we will relate fracture mechanics with solid mechanics, so that we can utilize this subject for tribology course. Coming to the fluid mechanics, there are two major type of the fluid mechanics topics in this. One is that pressurized one, self pressurization or external pressurization. This kind of the fluid which we are using, we can name this topic as hydrodynamic, aerodynamic, hydrostatic and aerostatic. By and large, hydrodynamic and aerodynamic mechanisms will remain same, only fluid and fluid property will change. In aerodynamic, we need to account compressibility of the air. So, governing equation will involve density term, while in hydrodynamic case density term can be avoided, because under pressure liquid is generally non-compressible, and that will simplify to some extent solution. Or in other words, aerodynamic solutions will be slightly difficult compared to hydrodynamic solutions. Similar case is with hydrostatic and aerostatic. Aerostatic means we are using some compressible gas, hydrostatic we are using liquid, but under external pressure, we are pressurizing from outside. While in case of the hydrodynamic aerodynamic, pressure is generated because of the relative velocity, is a self pumping action. Apart from these theories, we will be trying to relate the convective heat transfer coefficient. In solid mechanics, generally conduction is treated, while in fluid mechanics, convection heat transfer can be treated properly. We will be studying some rheological behavior of liquid. We know viscosity will vary under temperature, under velocity or sliding conditions. We will be studying the liquids along with semi-liquid. Let's take a typical example of the grease. Grease is a semi-solid substance. If we want to lubricate bearings with grease, we need to have a rheological model, and to use that rheological model, we need to understand fluid mechanics. We will be studying something like a boundary lubrication, mixed lubrication and elastrohydrodynamic lubrication. Typical example given for the elastrohydrodynamic lubrication is rolling element bearings, gears, and easiest way to study the elastrohydrodynamic lubrication is that there is a roller or cylinder sliding against a surface. It may be convex surface, concave surface or flat surface, but for mathematical treatment we can always make a pair with one convex surface and other flat surface. Same theory can be utilized irrespective of whether flat surface, convex surface or concave surface by changing effective radius. That means, if we understand effective radius model, we can utilize or we can analyze all kind of machine elements under elastrohydrodynamic lubrication. As I earlier mentioned, viscosity is a function of temperature. Increase in the temperature, viscosity will decrease, but it is only for the liquids, it is not for the gases. In gases, under high temperature condition, more and more molecular activity will occur, that will create more and more disturbance in flow paths, that will enhance viscosity. So, there is a basic difference between viscosity of gases and viscosity of liquids. When we pressurize lubricant oil, it gets thickened. There is a possibility of viscosity increase under pressure, and we need to do mathematical modeling of this viscosity behavior. Apart from that, we will be doing some mathematical modeling related to thin film lubrication. May involve liquid, may involve gas, may involve solids, but if we want quantification, we need to do mathematical modeling. Coming to the material science, I can say material science has changed tribology significantly. By changing the surface properties, we can change wear behavior by many times. By just coating few micron coating on the surface, surface life can be changed or can be enhanced significantly. Take an example of simple needle which is used to stitch the clothes. If I do not coat with the chromium steel, it may get corroded, it will get blunt, it will not be useful, but just when thin coating on that needle enhances the life, maybe say 10 years, 20 years, and the coating thickness will not be more than 10 microns. Now, just changing material properties of the surface, we can increase the service life significantly. Similarly, we have seen cars, all cars are coated, maybe the Teflon coating that will provide a better look, better appearance of that car. So, if the coating changes drastically the service life of the component. The coating can be thin coating or thick coating, or it can be just a surface treatment, surface hardening like a shot peening. Shot peening increases the hardness of surface causes the lesser plastic deformation under subsequent loads. So, that enhances its properties to sustain wear or to tolerate wear. It makes substance or component much more wear resistant. We can go ahead with a number of high temperature coatings also. Sometimes we can use simple solid materials, say solid lubricant, and we can rub on the surface, get overall good results. Take an example of cam surface. If we rub cam surface with molybdenum disulfide powder, it will show much lower friction for at least couple of hours before that layer is delaminated. To firmly attach it, either we can use a carrier fluid along with the molybdenum disulfide, or we can use some manufacturing process to embed that particle on the surface, so that it cannot be easily removed from the surface. So, it is important for us to understand what are the manufacturing processes behind these coating technologies, or what are the different coating technologies. And again, if you want to quantify the tribological behavior of coating, then we need to model thin and thick coatings. Mathematical treatment is essential for that. Coming to the chemistry, that plays a major role, and in fact, many chemistry background people are good tribologists. Take an example of anti-wear additives developed by chemists. Take an example of surfactants developed by chemists. Example of extreme pressure additives developed by the chemists. But we can utilize these additives to enhance service life, to increase load carrying capacity of machine components. However, we need to understand what is the compatibility of these lubricants with process fluids. If we understand chemistry of process fluids, we can be utilizing those process fluid as a lubricant itself, or by adding some additives in those process fluids, we can avoid extra lubrication requirement. So, we need to understand the chemistry of the lubricant to do that. Understanding chemistry of the lubricant will give some knowledge related to the shelf life of lubricants and its additives. We know very well all additives have some shelf life. If oil is kept, it will get oxidized if it is not treated properly, and performance of lubricant is generally a function of temperature, sliding speed. If there is a too very high relative sliding speed, naturally there will be possibility of shearing of additives which are mixed with the lubricant. So, we know if we are going for a very high relative velocity application, we will be requiring quite different additives compared to additives required for the low speed operations. Further, understanding chemistry will help what kind of percentage or what percentage will suit overall requirement of lubricants. Many times we use just few percent of additives in lubricant, which may not be right. Sometimes 0.1%, 0.2%, because many times additives they conflict each other. Take an example of detergent. It will try to remove the surface layer from surface, while extreme pressure additives they get on the surface. If I mix these two without proper understanding, one additives will remove the surface and other additives will get attached to the surface, and overall result will turn out to be 0, no use. So, we need to have proper understanding between these two kind of additives. Once we have proper understanding, that will help us. Sometimes understanding of these additives require whether additives are getting attached to the surface due to covalent bonds, metallic bond or van der Waals bonds. So, modeling of these bonds, modeling of these forces is important for us. Let us take one of the very simple example and try to relate these subjects. I am just showing in this figure component 1, component 2. Now, we try to push component with some tangential force. What will happen? Due to irregular surfaces in contact, there will be number of barriers. Either these barriers need to be elastically deformed or ruptured, then only this top component can move related to this component, otherwise it will not be able to move. If it is ruptures, then there is a possibility of further generation of irregular surface, and if this happens continuously, machine component will lose its thickness in no time. However, if we use this properly, then there is a possibility that there is a low contact and lubricant layer is playing intermediate role, or lubricants, they are getting load, they are supporting load from component 1 and transmitting to other one. So, they are using as a cushion between two surfaces, or they are able to spread stresses more uniformly, more area comes into picture compared to low or lesser area due to irregular surface. And if I try to project this on a one curve, I say that I am trying to relate wear rate with the time, sliding time. What we get? Initially, there is a irregular surface, it will wear out, it will give more and more debris, but due to lack of further asperities and possibility that no uneven surface is generated at the other surface, there is a possibility of lesser wear and reaching to one steady state after some time. That is why we call this time 0 to this time as a bedding time. It may take few hours, it may take more number of hours, or may cause a catastrophic failure, depending how we are treating these two surfaces, how are we designing these two surfaces. We know very well after a long time again surface will wear out if wear is consistent. That may wear occur due to increase in clearance between the surfaces, lesser thickness remain after some time, or maybe some other reason. So, generally this bathtub curve is plotted or used to find out what will be overall life of the component. We need to do detailed understanding about these two components, how they will come in a contact, whether they are making any adhesive bond or not. If there is an adhesive bond between component 1 and component 2, then there will be excessive wear. Even if the one surface is very hard compared to other surface, what will happen in that case? Harder surface will scratch rough, softer surface. However, if the hardness of the two component is same and they have some sort of toughness and ductility, then this surface will asperities will simply tear away without generating additional surface problem on this other component, and this behavior will occur. But if we are using some ceramic components and there is a possibility of fracture of the asperities, very high rough surface will be generated after tearing those asperities, then there is a possibility that this two curves merge, this line and this line merge, removing this intermediate path. So, there is a possibility of failure in this. We will continue with this topic in our next lecture. Thank you for your attention.